Welcome to our next lesson. In this lesson, we are going to learn about the quantum numbers. We are going to have quantum numbers. Alright, quantum numbers. Okay. So here, our first quantum number, we need to consider the principal quantum number. The principal quantum number. The principal quantum number. Alright, so this principal quantum number often represented as small n. Alright, so here the definition is this is used to determine the energy levels or the number of shells present for a particular atom. For instance, if you have, let's assuming this is a given shell, this is the nucleus and then an orbit as described by Bohr. Alright. So here we have the first shell, which is the energy level K and then L. Because we are having two shells here, we say that the principal quantum number here is what? 2. So we take n is equal to 2. That means we have two principal quantum numbers, or two number of shells. So this is, if we say the principal quantum number, we just mean the number of shells that we need to have, or the number of shells present, and it takes values from n equals 1 up to the the total number of shells that you want. Most of the times it's almost up to 4. All right. So here, as n increase, the size of orbitals also increases. So if you increase n, the size of this orbitals also increases. For instance, if I have another structure here, this is the first n, the second n, we can see that as we have added the second shell, we are increasing the size of this. Right. So if you add another shell to it, you see that the size or the size keeps on increasing. So here we are determining the energy levels for each shell. Remember that as closer as the electron is to the nucleus here, the greater the attraction occurs. All right. So it will require higher energy to remove an electron on this shell, which is closer to the electrons than these ones, than the other ones. So here, when we talk about the principal, we are just talking about the number of shells that is present here. Okay, so let's take the another type of the quantum number. The next one is the azimutal quantum number. Azimutal quantum number. Alright, so this azimutal quantum number normally is represented as small l. What is that is that the azimutal quantum number is used to determine the types of orbitals in the main shell. The types of orbitals in the main shell. Alright, so here we take the types of orbitals. Remember from the chart cloud model that we got some orbitals, which is, or the suborbitals, which is the s, p, d, f orbitals. All these are support orbitals. So the azimutal quantum number here is telling us the number of suborbitals that we have. Alright, so here it ranges from L equals 0, 1, 2 up to n minus 1, where n is the principal quantum number. So for instance, if you have 3, n is equal to 3. If you have n is equals to 3, that's the total number of shells. If the total number of shells is what 3, it means that L azimutal quantum number is going to range from 0, 1, and then 2. It will end at 2, but the last one must be n minus what 1. So if we have 3 minus 1, that means we need to start from 0 and end at 3 minus what 1. If n is equal to 4, we need to range from where 0 and then end at 4 minus what 1, that is 2 and what 3. Alright, that means we are going to have uh, four different types of what 4 different types of suborbitals in the main shell. Alright, so that is the work of the azimutal quantum number, which is the small l. Okay, so here, for instance, what we do is that now, because this 0 is represented as the first azimutal quantum number on the electronic configuration, let's assume this is the first shell, K shell. If we have this n, this is n, our n, because it is the shell. So when n is equal to 1, it means that our L is going to range from 0, and then we end at 0, because it's up from what 0 to 1 minus what 1, which is the same as what 0. Alright, it means that we have only one particular or only one subshell present on this on this K shell or on the first shell, and this 0 here represent the s orbital, the suborbital called the s orbital, the s orbital. If you have n to be equal to 2, if you have n to be equal to 2, that means L is going to range from 0 and then ends at what 1, because 0 to 2 minus 1 is what 1. Alright, so if we have this, it means that we are going to have s, this 0 is for s, and then this one represent the p orbital. Alright, so it means that on this particular shell, which is the L shell, we have a suborbital s and what p. We have suborbital s and p. Okay, and also if you have 3 shells present, 3 shells, let's assume we have 3 shells present, that means we have the M shell, the third shell, that is n is equal to what 3, because the principal quantum number determines the number of what shells or energy levels present. Alright, so if n is 3, then the azimutal quantum number is going to range from 0, 1, and then ends at 2. Okay, so this 0 is for s, this 1 is for p, and this is the d orbital. The d orbital. It means that on this third shell we have s, p, and what d, s, p, and d orbital on the third shell. Alright, so if we have 4, that means if we have n to be equal to 4, let's assume we have 4 number of what shells. Alright, so here if n is equal to 4, then L is going to range from 0 to 3, that's 1, 2, and what 3. That means on that main shell, which is the last what shell, on the valence shell, we have s, p, d, and what f. So here we are going to have suborbital s, p, d, and also what f on this what main shell when n is equal to 4. So that is if the quantum number or the principal quantum number is what giving us what a particular number. Let's say if it is 3, then the azimutal quantum number will give us what it will range from 0 to 2, and it determines the type of a suborbital